When describing the refractive indices of uniaxial minerals, it's necessary to discriminate between the O and the E ray and to be able to recognize when the mineral is properly oriented so that you are observing only the O ray or only the E ray. And in order to do this, we use a visualization called an indicatrix. And visualization is an imaginary, the indicatrix is an imaginary three-dimensional ellipsoid. And it's used to define the refractive indices and the birefringence of these individual plane polarized components. And it's actually used in all anisotropic crystals, not only in uniaxial crystals, but also in biaxial crystals. In biaxial crystals, it's a bit more of a complex geometric body. Well, the indicatrix looks like this. It's a ellipsoid, and it's an ellipsoid in which its dimensions are defined by measurements from the center of the ellipsoid body to the edge. For example, omega is measured in this horizontal sense from the middle of the ellipsoid to the edge of the ellipsoid, the dimension omega. Epsilon is measured in the vertical sense from the center of the ellipsoid to the top of the ellipsoid. Now, the section, the horizontal section like this is actually circular, so that omega could specify this direction as well. So this is a, for this particular case of the mineral, it's a positive mineral where epsilon is greater than omega, and so this body is elongated in the vertical sense. Now, the other thing you need to remember for uniaxial minerals is the position of the C-axis. So the pencil then now shows the position of the C crystallographic axis for tetragonal and hexagonal minerals. These are the minerals that are uniaxial. It's always got this vertical sense of orientation. That is, that the extraordinary ray, or the E ray, is parallel to the C axis in these particular minerals. So the point of this indicatrix then is that for any particular orientation of the mineral on the microscope stage, we imagine a section through this indicatrix, in fact cut through the center of the indicatrix. And this means that any particular mineral grain then represents a slice of the indicatrix. For example, let's look at what a vertical section of the indicatrix looks like. Here is a vertical section, and again, it's a positive mineral with a positive sign, so that epsilon is greater than omega, and so the ellipse is elongated in this vertical direction. Remember that the C-axis is located right here. If you have the mineral in this orientation, then you can say that the C-axis of that mineral is lying effectively on the stage. And the epsilon refractive index measured here, omega measured in this direction. Now, these things also represent the position of the E and the O ray respectively. And so that when you have this section, this kind of orientation, or when the C-axis of the mineral is on the stage, then it's possible, if you can recognize the position where you are, to rotate the mineral grain until you have coincidence of one or the other vibration direction with the microscope polarizer. For example, in this position, since the polarizer on a Zeiss microscope is east-west, in this position we can examine only the extraordinary ray, or measure the epsilon refractive index. And if we rotate this mineral grain back to the vertical position, then we are prepared to examine only the ordinary ray, or the omega refractive index. Well, the other opposite kind of section that we have of the indicatrix is a horizontal section. The horizontal section of the uniaxial indicatrix is much simpler. It's a simple circle specified by one radius omega. And remember that in this orientation, this is the horizontal section, the C-axis is located perfectly perpendicular to this side of the figure. That is, it's exactly perpendicular to the stage if the mineral grain can be oriented in this kind of orientation. Well, that takes care of a positive uniaxial mineral. What does the indicatrix look like for a negative mineral? Here's the negative kind of case. It's a very similar kind of geometric body, except that the difference now is that the ellipse is more elongated in the horizontal sense. That is, omega in this particular case, and some mineral is negative, omega is larger than epsilon. So it's squashed in the vertical sense. The c-axis is still located here, but now the epsilon refractive index is less than omega. The E-ray still has this kind of orientation. And this means then that the horizontal section of this figure looks exactly the same. It's a circle with the radius omega, but the vertical section looks different. And it looks essentially like this, a flattened ellipse with omega measured here in the horizontal direction, epsilon measured in the vertical direction. And again, to examine epsilon, what you need to do is rotate the mineral grain until the E-ray, or the E vibration direction, is parallel to the microscope polarizer. Or if you had this mineral grain and you knew its orientation, then you would have to rotate the mineral until the E-ray was in an east-west position parallel to the microscope polarizer. Okay, well, how do we recognize different kinds of orientations of the indicatrix? To do this, we have to use something which is called an interference figure. Now, an interference figure is what you see when you look at the mineral in conoscopic view. Now, let's look at some uniaxial interference figures then. And in order to do this, I want to set up the microscope properly for an interference figure. And to do this, then, we need a particular mount, and I'm going to start with a mount of a thin section with including many crystals of the mineral quartz. Now, in preparation for the interference figure, first you have to find a large mineral grain within the field of view. And once you find this particular mineral grain, then you want to use your high power objective. You also want to look at the mineral using the converging lens and the Bertrand lens. And you need also, of course, to provide the maximum amount of light that your microscope can provide. You also always look at interference figures with the polars crossed. So if you get your mineral grain in focus, you get your, before you put in the converging and Bertrand lens, you get the maximum amount of light, you get your objective centered. All these things are very important. Then you can put in your Bertrand lens, put in your converging lens, and look for an interference figure. And what you see, if you haven't looked at an interference figure before, is very surprising. And this, for example, is a interference figure off the mineral quartz. This is a very special kind of interference figure. You tend to watch these interference figures during stage rotation, and actually I'm rotating the stage in this orientation now, and you can see very slight kind of movement. The form that we see is essentially looks like a black plus sign with the black portions of the interference figure roughly parallel to the north, south, and east-west crosshairs. This kind of figure is called a uniaxial centered optic axis figure, or it can be abbreviated as a COA figure. And this is the kind of figure that is obtained when the C-axis is perpendicular to the stage of the microscope, or when we're looking at the circular section of the uniaxial indicatrix. The two black lines that we see in this interference figure are called isogyres. Isogyres are the black portions of interference figures. And this kind of figure shows two isogyres, which are crossed in the form of a plus. They move slightly, but they remain almost stationary. Now, the refractive index that we can examine in this kind of orientation from this kind of figure is the refractive index omega. And because the section of the indicatrix that we're looking at is circular, the orientation of the stage of the microscope matters not at all. And we can measure omega in any orientation of the stage. Well, let's look at the same kind of interference figure now for the mineral calcite. And the feature of calcite that's important here and that influences the character of the interference figure is that there's very large difference between the omega and the epsilon refractive index. And so we see here now with the centered optic axis figure a very large number of color curves. And this is due to the very high birefringence of the mineral calcite. So that the number of color curves that you see in a particular interference figure is really measuring the retardation. And if the mount is the same size, then of course it tells you about the birefringence of the particular mineral. So these are uniaxial centered optic axis figures as shown on mounts that show increasing kinds of retardation. Well, let's now look at the kind of interference figure that we obtain if we cut the vertical section of the indicatrix. So I'm going to go back now to our quartz mount. And this time we're going to look at a mineral grain in which the C-axis of the quartz is actually lying on the stage of the microscope. And the kind of interference figure that we see in this sort of orientation is very different. Now we're looking at the interference figure, and you can see what it looks like. During most of the period of rotation, you see an illuminated field, in this case a white or creamy white colored field, but during a very small degree of rotation, the isogyres actually enter the field of view and leave again. And if you watch closely, you can see that they enter from one direction and leave from another direction. This kind of figure is called a uniaxial flash figure. And when you see this kind of interference figure, it tells you that the grain's orientation is such that the C-axis is parallel to the stage of the microscope. Uniaxial flash figure. Now I'll look at a flash figure, for example, on the mineral calcite, which has, of course, higher birefringence. And you can see that the character of this flash figure is very, very similar to the character of the flash figure on the quartz grain. So, uniaxial flash figure. But what happens if we have a more or less random kind of orientation? I mean, both of the sections that we've talked about, the horizontal section of the indicatrix and the vertical section of the indicatrix, are very special kinds of orientations. What happens if the C-axis has some angle to the stage? And this is the normal kind of randomized mount. Then what kind of figure do we see? And I'm going to show you a series of different interference figures depending on the different kind of orientation and how close the C-axis is to parallel or perpendicular to the stage. So first of all, this is again a mount on a thick section of quartz, and so there are some color curves that show in this mount. What we see here is an uncentered figure, a typical uniaxial uncentered figure, and now we can see the two isogyres crossing in the field of view, but the point of intersection is not at all centered on the crosshairs of the microscope. In fact, you can see that it rotates and migrates around the field of view as we rotate the stage of the microscope. So this is an uncentered optic axis figure of a uniaxial mineral. Now I'm going to move and look at another grain which shows a orientation that is still more uncentered in the field of view. And now the point of intersection of the isogyres is actually outside of the field of view. This is a case where the c-axis is at a very high angle to the stage. That is, it's nowhere near a perpendicular kind of orientation. So we have all degrees of uncentered figures, as you would expect, and it really depends on the orientation of the c-axis. How large an angle does the c-axis make with the stage of the microscope? This is what governs the character of the uncentered kinds of figures. Well, let's summarize the orientation relationships then of these different kinds of uniaxial figures. We obtain a flash figure when the c-axis is precisely parallel to the stage of the microscope. This is the kind of figure where we barely see the isogyres, just 4 times during rotation. We see them, they come into the field and go very rapidly out of the field. We have another kind of special figure that occurs on the horizontal sections of the indicatrix, or the circular sections of the indicatrix, when the c-axis is exactly perpendicular to the stage, and this is called a centered optic axis figure. And the most common kind of figure then we call uncentered, and it's a quite variable looking figure and occurs when the c-axis makes some other angle to the stage, not perpendicular, not parallel to the microscope stage. Now, there's a very close relationship then between the kind of figure and the refractive index that we can measure in that particular figure, and this diagram tells us which refractive indices we can measure depending on which figure we obtain. If we could obtain the flash figure, then it's possible for us to measure both epsilon and omega in that particular figure. If we obtain a centered optic axis figure, the only refractive index we can measure is omega. And if the figure is uncentered, we have some other section of the indicatrix, and we can measure omega, and we can measure some other refractive index which is actually not epsilon or not omega, but some value in between. We call this refractive index epsilon prime. Well, how do we tell the orientation of epsilon and omega? We can use the figure to tell us information about the uniaxial mineral. For example, let's go back to our quartz mount and our centered optic axis figure of quartz. And now we're looking at this centered optic axis figure. When we obtain a centered optic axis figure, we can directly determine the sign of the mineral by using the accessory plate. And so I'm going to take the accessory plate now and insert the accessory plate into the accessory slot and look again at the centered optic axis figure. And now you can see that for the mineral quartz, in the northeast and southwest quadrants of this particular figure, we see, with the gypsum plate, we see a blue color. And in the northwest and southeast quadrants, we see a yellow color. This is telling us that there is addition of interference colors in the northeast direction. There is subtraction in the southwest direction. And this is the test of optic sign using a centered optic axis figure. That is, we use the accessory plate and we look for addition or subtraction in the northeast quadrant. If there is addition in the northeast quadrant, then the mineral has a positive optic sign. This is telling us then that the epsilon refractive index is greater than omega, and also that the E ray is the slow ray in this particular mineral. So quartz, being a positive optic uniaxial mineral shows a positive sign in this kind of direction. Now, I'm going to switch now to the mineral calcite to show, again, a centered optic axis figure, and to demonstrate the determination of the sign when we have many color curves. In this particular case now, instead of using the gypsum plate, we use the quartz wedge. And we insert the quartz wedge and watch the movement of color curves, again in this northeast quadrant. Because calcite has such a high birefringence, the quartz wedge is much easier to use, so we now insert the quartz wedge and we watch the movement of the color curves. And you can see that as I insert the wedge, as I'm doing now, the colors move away from the center of the northeast quadrant. That is, the color curves expand. The color curves expand in the northeast quadrant, they contract in the northwest quadrant. So now I'm inserting the quartz wedge, and you can see the expansion of colors in the northeast quadrant and the contraction in the northwest. Well, you have to watch this northeast quadrant. If the color curves expand, we say that the colors fall. The color curves expand in the northeast quadrant, we say that the colors fall. And if the colors fall, then the crystal has a negative sign. Calcite has a negative sign. Its epsilon refractive index is less than omega. Now, the opposite of this kind of test then would show the color curves contracting in this northeast direction. And if the color curves contract, we say that the colors rise for the crystal, and that the optic sign of the mineral then would be positive. If the colors rise, the optic sign is positive. Now, we can take any kind of uncentered figure and also determine the optic sign from an uncentered kind of figure. For example, let's look again at the amount of the mineral quartz, and I'll obtain a typical sort of uncentered figure. And again, you can see the orientation of the isogyres, and I simply rotate this uncentered figure so that we're looking at the northeast quadrant of the interference figure, that is the northeast side of the intersecting isogyres, and I can again use the accessory plate, and I'll use the quartz wedge in this particular orientation. And you can see that in this particular case, as I insert the quartz wedge, now I'm inserting the quartz wedge, the color curves are contracting. The color curves contract. This is an indication that the mineral quartz has a positive optic sign. The colors are rising because the color curves are contracting as I insert the quartz wedge, so the crystal is positive. The mineral quartz then observed in an uncentered optic axis figure and the determination of the sign of the mineral. But we can also get the sign of the mineral. And of course there are two possibilities, a positive or negative kind of sign, and this is we can use as an identification criteria. So we want to know the sign of particular uniaxial minerals. We can also get the sign from a flash figure. So let me demonstrate this using a flash figure on the mineral quartz. So we'll look at this flash figure. And you can see, if you watch this flash figure, you can watch the departure of the isogyres from the field of view. And as I rotate the stage, if you look at this figure closely, it's a vague kind of figure, but I think you can see very clearly that the isogyres first leave in the northeast direction. Now as I rotate again, they are now leaving in the northwest direction. Now they leave in the northeast, now in the northwest direction. And in other words, there's an alternating direction of departure of the isogyres. Well, you can use this dynamic test as I rotate the stage and watching the direction of departure of these isogyres to indicate in this flash figure orientation the position of the E ray. In other words, these isogyres leave in the direction of the E vibration direction. And so that as the isogyres leave in the northeast direction, it is telling you the direction of the E ray in the mineral. So we use this and we rotate the mineral grain to show the departure in the northeast direction. Then we stop. So we see the isogyres depart in the northeast direction. We stop and we remove now the converging lens and the Bertrand lens of the microscope, and we look at the mineral now in crossed polarized light. And so now I'm looking at this particular quartz grain in cross polarized light. I haven't changed the position of the microscope stage, kept the microscope stage in the same position so that it's left. We know the isogyre is left in the northeast direction, so we now know the position of the E vibration direction. Now I look at the mineral grain in cross-polarized light. I see a white interference color. The white interference color then can be tested looking at the gypsum plate. I insert the gypsum plate. Now I know that the E vibration direction is located here in this northeast quadrant. I know that the slow direction on the gypsum plate is also in the northeast quadrant. So I insert the gypsum plate and we look now at the mineral grain in cross-polarized light with the accessory plate, and you can see that it shows now a blue interference color. This indicates addition of colors. And if it's addition of colors, then we know that the E ray is the slow ray. It has added to the slow ray of the accessory plate. There's been addition of colors. And in order to prove this, let me simply rotate the stage now. I'm going to rotate the stage 90 degrees. In other words, I'm going to rotate it so that the E ray is now in the northwest direction. So I'll turn it back and we'll watch the rotation within the microscope. Now I'll rotate the thing 90 degrees now, and so we're looking at the slow ray of the mineral is now opposed to the slow ray in the accessory plate, and you see a yellow color which indicates subtraction. So we can determine then the sign of a uniaxial mineral from the flash figure. If we note the position of departure of the isogyres within the figure and use that as a guide to the position of the slow ray of the mineral. I should say the E ray of the mineral. Then we can test with the accessory plate to find out if E is the slow ray, in which case the mineral is positive, or if E is the fast ray and the mineral is negative. So you either see addition of colors with the accessory plate or you see subtraction. Well, let me demonstrate the same test now using the mineral melolite. And so we'll obtain a flash figure here on the melolite grain, which tells us that the C-axis, of course, is lying on the stage, and we observe the departure of the isogyres and wait for the case where the isogyres depart in the northeast direction, as they're doing here, and stop the stage rotation at that departure. And now we know then that the orientation of the E ray is in the northeast direction like this, and then we can use the accessory plate then to determine whether the slow ray in the accessory plate is parallel to the slow ray in the mineral melolite, or whether it's parallel to the fast ray. And the way we test that then is to look at the mineral simply in cross-polarized light, take out the Bertrand lens, take out the converging lens, insert the accessory plate like this, and watch the change in color. So I'm going to pull it out again, and now we'll look at the mineral melolite in cross-polarized light, and you can see again it shows a white kind of color. As I insert the accessory plate here with the slow ray direction control, the color changes to yellow. This is indicating subtraction of colors and the fact that the mineral melolite has a negative optic sign. And again, I'll rotate this mineral 90 degrees so that the slow rays are now parallel, and you can see addition of colors. So when there's subtraction of colors, then you know that the E is the fast ray in this particular mineral. The mineral has a negative optic sign. Well, it's also possible to use the interference figure to describe the color of the mineral or the pleochrism of the mineral. Because if we can find the E ray, then we can tell whether the E ray's absorption is stronger or weaker than the O ray's absorption. Now let me demonstrate this on the mineral tourmaline. So I'll put a tourmaline thin section on the stage here, and we'll look at the tourmaline now in plane polarized light, and you can see the pleochrism in these elongated tourmalines that occurs as I rotate the stage. As I rotate the mineral grain, then you can see the color change. The mineral has a very, very strong color in one orientation and a much weaker color in another orientation. Well, if we take the same mineral grain now, while we're looking at it, and change to our high power, increase the light, look at the mineral in conoscopic view, and obtain a interference figure. And here we can see that the interference figure on this particular grain is a flash. And upon rotation, you can see again the isogyres first leaving in the northwest direction, now in the northeast direction, northwest, northeast. This tells us again the direction of the E ray. So as I rotate this thing then until the isogyres leave in the northeast direction, like this, I now stop the rotation and I know that the direction of the E ray is precisely to the northeast, just like this. Then what I want to do is remove the Bertrand lens, remove the converging lens, remove the polarizer, and look at the mineral now simply in plane polarized light. And so here's the mineral grain now with our E ray still in the northeast direction. Now the procedure then is to rotate the mineral grain until that E ray, which I now know is toward the northeast direction, to rotate it until that direction is exactly in an east-west position, parallel to the microscope polarizer. So I'll now do that. I'll take it from the northeast direction and rotate it until it's exactly parallel to the microscope polarizer. In other words, do this kind of rotation to it. So now I'll do that under the microscope and do this rotation. So I've got the E ray now is exactly in an east-west position and exactly parallel to the microscope polarizer. And here you can see that the color of the tourmaline is very weak. And compare this color to what the color is when I turn the E ray to the north-south direction. So I'm going to rotate it so that the E ray is now in a north-south kind of position. Okay? I'll repeat that rotation into the north-south position. Now the E ray is north-south, and the O ray is receiving all of the light from the plane polarized direction of the microscope polarizer. Here the color is much stronger, and the greater absorption that occurs in the O direction then allows us to characterize this kind of pleochrism as being O greater than E. So tourmaline has the absorption formula, which we call O greater than E. And we can use this absorption formula to help identify the mineral tourmaline. It's one of the few minerals that has the absorption formula O greater than E. That the color is stronger in the for the O vibration direction than it is for the E vibration direction, or that absorption is greater in the O direction. So most uniaxial minerals have the opposite formula, the formula of E greater than O, but tourmaline has the formula O greater than E. And the only way we can make this determination is by using the interference figure to test the position of the E ray. Okay, well, we can use the interference figure to show us the position of the E-ray, and so that we can actually determine the epsilon refractive index. The minute we see the isogyres leave from that flash figure, then we know that the position of the E-ray is either in the northwest quadrant or the northeast quadrant, depending on which way they left, and we can then rotate that direction until it's parallel to the microscope polarizer, and then we know that all of the light from the microscope polarizer is being resolved into the E direction. If we rotate it 90 degrees, then we have all the light being resolved into the O direction. So I just want to remind you again that if you want to determine these index of refraction, epsilon and omega, you need to pay attention to what orientation you have, which is told by the interference figure. The flash figure, you can get both epsilon and omega. In the centered optic axis figure, only omega. In the uncentered figure, omega and epsilon prime, which is a refractive index somewhere between epsilon and omega. Well, you can also relate the birefringence of a particular mineral grain to the kind of interference figure that you obtain. And this chart summarizes that relationship. In a particular mineral, if it has the same thickness, we'll show its maximum retardation when it is in the flash figure orientation, or when the c-axis is lying on the stage. And in other words, the birefringence of a particular mineral reaches its maximum in the flash figure orientation. It reaches essentially a zero minimum when the c-axis is perpendicular to the stage. That's the centered optic axis orientation. And the birefringence is generally intermediate between the maximum and zero in the uncentered kind of orientation. Now, in fact, we can use this relationship to help us pick mineral grains in a particular mount. I want to demonstrate this with a thin section of the mineral quartz. And this is a quartz sandstone, which I'm going to look at. And this sandstone is full of quartz grains. So we see a diverse field of quartz grains, and I'm going to look at these now in cross-polarized light. And so as I look at these quartz grains in cross-polarized light, you can see a considerable variation in the interference colors which these quartz grains show. That is the maximum interference color. For example, this particular grain, even though I rotate the stage throughout a large degree of rotation, its maximum interference color is only a very, very weak gray color. This indicates that this particular mineral grain has its c-axis nearly perpendicular to the stage. It only develops a very, very low birefringence. And yet nearby, here's another quartz grain that shows a very nice creamy white, almost a yellow interference color. This is one of the highest interference colors shown by any of the quartz grains. And this tells me that this particular quartz grain has its c-axis nearly parallel to the stage. Its maximum interference color. And this grain is much more likely to show a flash figure. The assumption here then is that the thin section has a common thickness, and that the differences that we see in the retardation of these mineral grains, which is indicated by the interference color, is primarily a function of their orientation. And in most thin section mounts, this is more or less a valid assumption. So you can look for grains that will show you a optic axis figure, like this grain over here, by looking for grains that show low retardation. And you can look for grains that are likely to show you a flash figure by looking for those grains which seem to show very high interference colors indicating high retardations.